So today I'll be presenting my research for my PhD defense on safe and efficient inverse reinforcement learning. So a lot of this work is motivated by the fact that we as people live in a very complex and wonderful world with a variety of tasks that we're interested in doing. Everyone has a variety of different preferences that they like to work under. And the goal here is that we want our friendly Mr. Robot, or more generally, any kind of autonomous system, to be able to enter our world and engage with people in a variety of different tasks under a variety of different circumstances and preferences. And it's very hard to program, robots or computer systems in general to be that flexible. And I think this really motivates this idea of imitation learning or learning from demonstrations, where similar to how people learn in different environments by looking at examples of how to perform a task, ideally we want our robots and our computers to be able to do the same thing. We're given some examples of how to perform a task. They can come up with a policy, which I'll denote by pi, that allows the system to be able to act in the environment similar to how the human wants them to. And so a lot of this work is based on, or kind of builds on this idea of reinforcement learning. So I'm going to quickly go over just kind of the basics of that. So in general, in reinforcement learning, we're going to model the environment as this Markov decision process, where we have an agent interacting with the environment, and the agent takes actions, and then that changes the state of the world, and it receives a reward given the state. And so for example, if we have an agent that we're trying to train to play this Atari game of Breakout, our state is going to be this information about where the bricks are, where the ball is, where the paddle is. Our actions are going to be the actions that we can take, moving left, right, releasing the ball. And then the main part of reinforcement learning, or I guess kind of a critical part of it, is this idea of reinforcement, this reward function. In this case, the score that the agent receives, telling it how well it's doing. And ideally, the agent wants to find a policy that maps from states to actions that maximizes its total reward. So today we'll be focusing on the idea of imitation learning, where we kind of take the idea of having an observer that's watching, say maybe a person, play this game. However, rather than having this explicit reinforcement, they're just observing the agent, perhaps seeing just the states, or maybe the states and actions taken by this demonstrator. And then they want to use that to come up with a policy that allows them to perform this task. And imitation learning is a really broad field. For the purposes of this talk, I'm going to kind of roughly divide it into these two different areas. The first on the left is behavioral cloning, where I see this as kind of answering the how question. How should an agent act in an environment? Typically, it involves trying to mimic the demonstrator by looking at the states and actions in the demonstrations and learning a mapping from states to actions. This is often pretty computationally efficient since it's a standard supervised learning problem. However, it can suffer from compounding errors. On the other hand, there's this idea of inverse reinforcement learning, which I see as kind of answering the why question, where we're trying to have this agent explain the demonstrator's behavior by recovering this reward function or utility function that's trying to capture the demonstrator's goals and intent. And now this can often be pretty difficult because we not only have to infer this reward function, we then have to solve this reinforcement learning problem or policy optimization problem afterwards. However, it has the potential of much better generalization if we really understand the why about what the human or the demonstrator is doing. And this talk, we're going to be talking a lot about safety. And I'd argue that if we want agents that are safe, we really want agents that can kind of think about the why, that can understand goals and intent rather than just going through the motions. And to kind of drive this home, I think we also want to have agents that have this distribution. So rather than just trying to recover a single reward function, I'm going to argue that we want agents that can reason about uncertainty as well, kind of proposing this Bayesian approach. And so to drive this home, imagine, if you will, a robot trying to make breakfast for someone, but just kind of going through the motions without really any understanding about why it's doing things. And this results in this epic fail of a robot trying to make breakfast, but really not accomplishing any of the underlying goals. And so I like this video. It's definitely designed to be satire, but I think it really drives home the point that no one's going to want to work with a robot like this. Ideally, we want robots that can perform well with high confidence. And for the purposes of this talk, I'm going to define safety in that way as this idea of correctness and confidence, where we want to have some measure of performance that ideally we want these agents to meet or exceed. And we want them to have typically a probabilistic guarantee of correctness. And I think if we want to take imitation learning systems out into the real world, it's really important to have this idea of safety, to have agents that can say with high confidence what their performance is going to be, and then use that to know whether they should get more help from a human, whether they're okay to actually run their current policies in the environments. And so the fundamental question that my dissertation seeks to address is this idea of how can an autonomous agent efficiently infer the intent of a demonstrator and provide safety guarantees in the form of high confidence bounds on performance. And so to answer this question, we're going to look at several different steps. First, we're going to start off with just explaining a general framework for safe imitation learning. And this will be work that was in my proposal, so we're going to kind of cover that in brief. Next, we'll talk about this idea of trying to do efficient reward learning from suboptimal demonstrations. We'll talk about how to scale some of the earlier ideas in this talk up to more complex tasks for performing the safety with these high confidence bounds. And then at the end, we'll talk about some ideas for robust policy optimization and risk-aware active learning. So the idea of safety, as we've talked about before, is we want to have these high confidence bounds. In particular, right now we're going to talk about how we can come up with an upper bound on the robot's performance loss with respect to the human demonstrator with high confidence. And I think kind of the crux of the problem here is that we don't know this ground truth reward function. We don't know the objective function. And so we're going to imagine that we have this policy, pi robot, that the robot wants to evaluate given some demonstrations. So if we talk about bounding policy loss, as I mentioned before, we're going to model the environment as this Markov decision process, where we have states, actions, and then there's some reward function R, that's the demonstrator's kind of underlying reward function. And if we knew that, we could calculate the value of a policy simply as the expectation over the sum of discounted rewards that we're going to get as we execute this policy. And if we think about policy loss, we can say, okay, what's the optimal policy under this reward function? So pi star is optimal. And then we can say, how much worse does our pi robot do compared to optimal when we're evaluating how much reward we obtain in this environment? So we want robots that can ideally answer questions like, how close is my performance to optimal? And so, as we talked about before, we want to have these high confidence bounds, ideally on performance. So given some small delta, we'd like our agent to be able to say, hey, with probability 1 minus delta, my policy loss is less than some value epsilon. But we don't know this reward function here, R. We also don't know pi star. So what can we do? One of the things that we can do is look at related work, and there are existing bounds that will try and answer this question. However, as I discussed in the proposal, and as you can see in the research document as well, these existing bounds are typically much too loose to be practical, often requiring tens of thousands of demonstrations to get a tight bound, which makes it impractical for most systems. And so as part of my dissertation, what we propose instead is to look at policy loss and reason about that under reward functions that are likely given the demonstrations, and really try and take a Bayesian approach. So as some background, there's this idea of Bayesian inverse reinforcement learning, which was proposed in 2007, where we're going to make the assumption here that our demonstrator is Boltzmann rational. So they're going to take good actions with higher probability than bad actions, and those probabilities are going to be related to how optimal those actions are. And so if we look at this equation here, we're going to assume that we have some inverse temperature parameter beta that determines how much confidence we have in the demonstrator taking the right action in different states. And so we can see here, this is giving us the likelihood, so the probability of a set of demonstrations D, given a reward function R, some hypothesis. Where Q star here is how much reward do I expect to see if I take action A in state S and act optimally thereafter. So kind of how good is action A in state S? And so we can see here we have this ratio of how good is what the demonstrator did, so our state action pair from the demonstration, compared to how good are the alternatives. So if I look at other actions the demonstrator could have taken, how good do those look? And so given some hypothesis, we want to evaluate this. And as you can see, reward functions that make the demonstrations look optimal, that have a bigger numerator, are going to result in higher likelihood scores. And this kind of matches our intuition that the demonstrations are more likely under hypotheses that would make the demonstrations look near optimal. So what we can do now is we can perform Bayesian inference in order to sample reward functions from this posterior. We can do this via a variety of methods. For the purposes of this talk, we're going to mainly focus on these particle sampling methods such as Markov chain Monte Carlo, or MCMC. Okay, so given that we can sample a bunch of distributions, a bunch of reward functions from the distribution over likely reward functions, we still don't know which one is right. And so what we propose to do is to use a risk-sensitive bound here to hedge against this uncertainty under which hypothesis we think matches the intent of the demonstrator. And so to kind of roll this out, so we assume that we start with some demonstrations coming from a Boltzmann rational demonstrator and a policy pi robot. We sample a set of reward functions that we think look likely given these demonstrations. Given any one of these reward functions, we can then perform this hypothetical where we can say, okay, how would the demonstrator have acted if R sub I were their true reward function? And then we can evaluate our policy and say, okay, what would our policy loss be under this hypothetical? So this gives us a sample of the policy loss from our posterior given demonstrations. And so we can then sample a lot of samples from this posterior distribution over policy losses given demonstrations. And then we can calculate any kind of a risk-sensitive metric on this. We chose in our earlier work to use the alpha value at risk, which is a metric from finance, which basically is the alpha quantile. And so if alpha is high, say like 0.95, this is going to find the 95th percentile worst case outcome. And we can use this to come up with a high confidence bound on our value at risk policy loss for any evaluation policy. And as I discuss in the research document as well as in the proposal, this results in orders of magnitude more efficiency in terms of number of demonstrations than prior state of the art. So it enables us to get tight confidence bounds on our performance given a limited number of demonstrations. And so this is nice. Kind of one of the takeaways from here is that we can get practical safety bounds now for policy loss from imitation learning given a small number of samples. And this really is nice because it allows an imitation learner to reason with high confidence about its own performance. However, there are some limitations that we're going to address in later in this talk. And one of the main ones is this idea of being computationally expensive. So to run Bayesian IRL, we're required to fully solve this MDP over and over again in order to calculate this Q star value to get this optimal policy under reward hypothesis. We're also generally assuming that we have a pretty good estimate of the optimality of the demonstrator by means of this confidence parameter beta. And while we may sometimes know how good the demonstrator is, often the demonstrator could have really bad performance and we might not know. And so we're going to look at how we can address these two concerns in the next section. We're going to look at how we can make reward learning more efficient and how we can actually learn from suboptimal demonstrations. And so the approach in this section is kind of motivated by these two concerns that typically inverse reinforcement learning methods can't do much better than the demonstrator because they're trying to find a reward function that makes the demonstrations look optimal. They're often also hard to scale to complex problems because, as we've mentioned, they often have this MDP solver on the inner loop that either fully or partially solves an MDP over and over again when performing reward inference. So what we instead proposed is that we could take a set of pre-ranked demonstrations. So if we have a set of demonstrations that the demonstrator has given some preferences over, what's nice is we can now find a reward function that doesn't make the demonstrations look optimal, but that explains the ranking, also potentially allowing us to extrapolate and perform better than the demonstrator. This also makes reward learning nice because we can now use these preferences over demonstrations to turn our reward inference problem into a supervised learning problem. There's a lot of related work here. I'll just briefly touch on some. So there's been a lot of work on active preference learning, which is very related to this, where often we're trying to find these pairwise preferences given queries to a demonstrator in order to learn a reward function. Most of these approaches don't take advantage of actual demonstrations and often require interleaving policy optimization with these active queries, which can result in really slow query time if it's a difficult policy optimization problem. Whereas in our approach, we're going to assume that we have some preferences up front, which allows us to avoid having this policy optimization that we repeatedly roll out to infer the reward function. And as far as I know, most of these approaches also don't investigate this idea of extrapolation potential from pre-ranked demonstrations, which we're interested in. There's also work on trying to learn from failures, where you use examples of failures to learn a better policy, which is similar to what we're going to do. Most of these approaches, though, don't consider a range of demonstration performance. They typically have successes and failures, and often require having an MDP solver in the inner loop, which we're going to try and avoid. So the method that we proposed, we named it Trajectory Ranked Reward Extrapolation, or TREX, as our fun acronym. And so the idea here is that we want to take a set of pre-ranked demonstrations So we have here this half-cheetah environment where we have this two-legged creature that's trying to run as fast as it can to the right. And you can see we have a set of demonstrations going from awful, where it's kind of inching along, to like mediocre, where it's kind of like this toddler running around and occasionally face planting. And ideally, we want to learn a reward function from these preferences, where we go from like worse to best. And then we want to optimize a policy, where here we show the policy optimized via this T-Rex that's able to run about twice as fast and far as the best demonstration. So how does this work? So if we're given any preferences, say a pairwise preference over these two trajectories, tau1 and tau2, what can we say? Well, ideally, if we sum up the rewards that we're predicting for the states in each of these two trajectories, we should have that the sum of rewards for the better trajectory is greater than the sum of rewards for the worst trajectory. So this means we can train a reward function that predicts rewards given states using just a standard Bradley-Terry pairwise ranking loss. And I think kind of a good intuition for this is to think about these cumulative returns as logit values and a classification problem, where we're trying to minimize the cross-entropy loss that enables us to classify which trajectory is better by running these trajectories through our reward function approximator and then seeing which one has the better return and trying to match our preference labels. This is nice because it's computationally efficient. It's a standard just classification problem. We've shown that it's sample efficient. We can learn from small numbers of ranked demonstrations, and it can often produce policies that are much better than the best demonstration. As we'll show, because of the simplicity, it allows us to scale this to high-dimensional visual control tasks. For example, here's an Atari game, where it's a racing game. You're trying to go as fast as possible and pass cars. Given 12 demonstrations, this is the best demonstration that's seen, which achieves a score of 84. Whereas our T-Rex method is able to learn a policy that scores 520 points and is able to navigate this racetrack much more efficiently, go much faster, and perform much better than the demonstrator. So you might be asking, so what if I don't have access to ranked demonstrations? So we've done some work here, where the first thing we looked at is, well, what if we're watching someone improve at a task over time? For example, what if we're watching this reinforcement learning agent? We don't have access to the reward, but we can kind of observe their behavior over time. So here I'm showing some checkpoints of an RL agent as it progresses in learning. As you might be able to tell, the goal here is to try and hop as many times and as far as you can to the right without falling. So the idea here is if I'm looking at someone improving at a task over time, I can make the assumption that on average, something later is likely to be better than something earlier if this agent is improving. This gives us weak preference labels, which enables us to run T-Rex. And we showed in the dissertation document, as well as in our paper, that this works really well when watching an RL agent learn at a task. Even though the agent is noisy, if it's improving kind of on average over time, this gives us pretty good rankings. We also looked at this idea of disturbance-based rankings, where we proposed DREX, disturbance-based reward extrapolation. But the idea is that we have a set of unranked demonstrations, and we perform behavioral cloning just to learn a policy from that. And then we create these automatic rankings via noise injection. So the more noise we add, here we're adding epsilon greedy noise. So with probability epsilon, the agent takes a random action. And the more noise we add, we can assume that on average, this is going to cause worse and worse performance, assuming that our demonstration is starting off significantly better than purely random. This gives us these weak preference labels, which we can then run through our T-Rex ranking loss to learn a reward function. And then use that and plug that into any reinforcement learning algorithm in order to learn a policy that we hope can perform better than the best demonstration. And we showed that over a variety of tasks, the DREX does consistently outperform the best demonstration, as well as other baselines such as just standard behavioral cloning, or more advanced methods such as generative adversarial imitation learning, or GAIL. However, we did notice some interesting things that would happen sometimes. For example, on the left here, we have Miss Pac-Man. So given a set of, I think, in this case, 12 ranked demonstrations from a human, this is what the agent learned to do. So it's kind of interesting and funny behavior where the agents really learned that, yeah, running into ghosts is bad, living for a long time is good, eating some pellets is good, but really, I just want to live as long as I can. And it's found this interesting hack where it can go back and forth between this little tunnel, which confuses the ghost and allows it to live for a really long time. And it thinks it's doing really good under its learned reward function. And it's not really matching the demonstration's intent. Additionally, for this space flying game called Beam Rider from Atari. The agents figured out if it goes left and right really fast, it can stay out of the firing lanes of the enemy ships, which is kind of a cool behavior, but it doesn't score any points. So I think this drives home the point that so far these methods we've talked about, DREX and TREX, are really just kind of finding a maximum likelihood hypothesis, and they may be overfitting to certain features in these ranked demonstrations. There's no notion of different hypotheses that might match the rankings, no notion of safety or robustness. So this is going to motivate trying to kind of go back to part A, where we were looking at this idea of these high confidence bounds on performance and seeing if we can scale these up to more complex tasks. And the idea here is that ideally we can combine the best of both worlds, where for TREX and DREX, these methods are typically much more computationally efficient than Bayesian IRL, can allow for better than demonstrated performance. However, the methods we proposed are just finding this maximum likelihood estimate of the reward function with no real representation of uncertainty. Whereas in Bayesian IRL, the classical version is typically very computationally inefficient. We're running this MDP solver over and over again. And it usually is trying to find a reward function that makes the demonstrator look optimal. But it gives us this nice rich posterior distribution over a bunch of different hypotheses that match the demonstrations, which enables us to think of more accurately about risk and uncertainty. So can we get the best of both of these? So to attempt to do this, we proposed, just last week we presented at ICML, this idea of Bayesian reward extrapolation. Where the idea here is that we want to take as input a set of ranked demonstrations, or more generally just preferences over demonstrations. And we're going to assume that our demonstrations are in this high dimensional visual space, such as learning to play like Space Invaders from visual demonstrations. And we're going to feed these high dimensional input states through a standard deep learning pipeline with a bunch of convolutional layers and embed them into a lower dimensional space. And the idea is we want to train this feature embedding such that it's rich enough that we hope that we can use it to predict reward functions. The way we do that is via these self-supervised task losses. So given demonstrations, we train it via a variety of methods, such as an autoencoder, where we're trying to go from a state, embed it, and then recover the same state. Temporal distance, where we take two different states from the same trajectory and try and predict how far apart they are. Inverse dynamics, where we try and predict the action that led to a state transition. And forward dynamics, where we try and learn a model that will simulate forward the state. And these all share the same feature embedding. And we also looked at adding the TREX ranking loss on there as well. So the idea is we can train this as a pre-training step. We can then freeze all but the penultimate layer of weights. And this gives us a feature embedding, which I'll call phi of S. And this allows us to then represent the reward function as this linear combination of these learned features. So why do we want a linear reward function? One of the reasons is this makes Bayesian reward inference much faster. So if we have a linear combination of these features, so some weight vector dotted with this feature vector, if we look at the return, the expected, or the sum of rewards over a trajectory, we can just plug in what the reward is and then pull out this weight vector, which gives us this dot product between the accumulation of features over this trajectory and our weights. So what's nice is we can take these ranked demonstrations, we can first pre-process them to embed them into this latent space, and we can save these values so we don't have to pre-compute them over and over again. So now the idea is we want to run Bayesian inference. We're going to be running this sampling-based method, MCMC, where the idea is we want to take a sampled weight vector, and we want to calculate how likely is this hypothesis given our preferences over demonstrations. So one way we could do this, our hypotheses that we sample could be just an entire reward function where we tweak all of the weights in the neural network, and then we could use just a standard kind of Bradley-Terry ranking loss, like what we did for TREX and DREX. However, if we change the entire network, this means every time we evaluate a hypothesis network, we have to run possibly really long trajectories through a really large network. And this can be really costly. Instead, if we assume that we have a linear reward function, we can pre-compute these sums over features. And now our likelihood function is just the result of several dot products. So it's much more efficient. And I should note that, once again, there's no MDP solver or model required here. We don't have to actually roll out any trajectories in the environment in order to get these reward function distributions, which is a really nice feature. So given that we have this likelihood of preferences, P, and demonstrations given some weight vector, We can then repeatedly sample for different weight vectors in order to draw samples from this distribution of likely reward functions given these ranked demonstrations. This allows us to generate up to 100,000 samples in just several minutes, just running on my laptop with no access to a GPU. Whereas if we were to run standard Bayesian IRL that actually tries to solve the MDP, this could take 10 plus hours to generate a single sample. And so we're achieving much better sample efficiency by taking advantage of this pre-processing, these pre-training steps, as well as these ranked demonstrations. So how does this perform when we want to learn a policy? So we looked at several different Atari games where we're learning from raw pixels. And here I show the normalized score based on the best demonstration. So 1 is best demonstration, 2 is performing twice as good as the best demonstration, and so on. And we looked at 2 different ways of training a policy given a distribution. One is to use the mean reward function from the distribution. The other is the MAP, or the most likely reward function. And both these methods work pretty well. They're doing much better than like a generative adversarial imitation learning approach, and can sometimes even perform better than a T-Rex approach that's learning just this point estimate of the reward function. However, having this rich posterior is really important for doing more than just learning a policy, given like an expectation of that posterior. We show that similar to our earlier work that I talked in more detail about in the proposal, that I kind of briefly summarized, we can actually perform these high confidence bounds now. So given a variety of different evaluation policies, we can come up with high confidence performance bounds to evaluate the risk of these policies. So how does this work? So we're going to assume that we have 2 different policies. We'd like to know which one we prefer given a distribution. What we can do is we can sample these reward function hypotheses and perform a policy evaluation for each policy to see how much expected return do I get under policy 1, under reward function I, as well as policy 2. And we can do this for all these different samples. In order to create these distributions over performance, well, we can now look at, say, like the tails and say, okay, which one has the biggest left tail, where this is plotting performance. And so something that has higher density in the tail is going to have higher risk. And this again motivates this idea of learning a linear reward function because it enables fast policy evaluation. We simply take any evaluation policy, and the expected return under that policy is going to be a weight vector dotted with our expectation over the features that we see. We can pre-compute that once by running one policy evaluation to get our expected feature counts. And then for every single new reward function, it's just a dot product to compute an expectation over feature counts. So this makes policy evaluation very efficient. And so this allows us to take a distribution and quickly come up with a distribution over performances from which we can calculate, say, like a 95% confidence bound on our performance. So one thing that's kind of interesting about this is we investigated whether this could be used to kind of detect these interesting and kind of weird reward hacking behaviors that we'd seen before. So for example, here we're given 4 different evaluation policies that weren't seen during training. And we're able to rank them pretty accurately in terms of the expectation over our posterior and these 95% confidence bounds. And these are the actual true game scores, which our agent doesn't have access to. You can see that the better the score, the better we're predicting them, as well as the better the lower confidence bound is. However, we notice that this is also highly correlated with the average game length. So as the games go longer, we're predicting better and better scores. So one thing we could do, one thing an agent could do, is it could learn, hey, I just want to live for a long time, so I'm going to run this no-op policy here. Where I just like don't touch my controller. I just fly along. Eventually, I get shot by an enemy. And then rather than clicking the button to keep on continuing to the next level, I just sit there, I'm still playing, and it looks like I'm doing really good. And in fact, yes, under the posterior, we do have a really high expectation. But I think the key thing to note here is that our 95% confidence bound is extremely low. And so I think this is a really good indicator for an agent that something's kind of fishy here. This looks like it could be really good in practice, but I have a lot of risk. My 95% confidence bound is really low. And so while this policy may look good under some hypotheses, there are also some hypotheses out there that make this look really bad. We also looked at a variety of human demonstrations where here's an example of me playing, I don't know if you call it good, but an okay game of Beam Rider, where I'm trying to actually play the game, shoot the enemy ships, but avoid getting shot. Here's an example of me playing the game okay. Occasionally I get hit by bullets. And then I tried to generate a deceptive demonstration where I'm trying to fly around, move, shoot, but not actually destroy any enemy ships. And then we have a pessimal policy here where I'm just trying to get hit as quickly as possible. And given these high confidence bounds, we are able to accurately rank these policies from best to worst, despite having this deceptive demonstration here that may look like gameplay, but it's not really destroying any enemy ships. So that's nice. Let's see. There we go. Okay. So another question you might have is, what if these demonstrations are extremely suboptimal? And this, I think, is clearly shown by this example here where we have a breakout agent where the best demonstration is only able to score 32 points. We're able to learn a pretty good reward function from this. And here's the policy that's optimized via Bayesian Rex, where we found, I think in this case, it was the average reward function, and then we ran that through a reinforcement learning agent. You can see that this agent is observing states that are really far out of distribution compared to our best demonstration. It's hitting bricks up on the top, which an agent has never seen whether that's good or bad. We also wanted to compare against a no-op policy again that just lets the ball go past it and then never chooses to release the ball again. So it's still playing, just kind of sitting there. And so as we would expect, both of these policies have pretty good expectations because they run a lot longer than the demonstrations, but they both have these low 95% confidence bounds. In particular, this Bayesian Rex policy, which actually is performing well, looks like it has really high risk because it's seeing all these states that the agent has a lot of uncertainty over. So I think this naturally motivates this idea of putting a human in the loop and asking the human for a couple active queries. For example, how would you rank this no-op policy and this Bayesian Rex policy compared to the previous policies that were ranked? And so given just simple labels like Bayesian Rex is the best, no-op is the worst, we're able to quickly recompute this posterior distribution, which quickly adjusts the agent's belief such that the 95% confidence bounds now actually do match the human's intention. And I should note that this only requires quickly rerunning MCMC. We use the same pre-trained features, and this is a very fast process. Okay, so we also looked at this idea of kind of an ablation. So what if we have like a low dimensional MDP with known features, and we still run this kind of ranking-based reward extrapolation to get our posterior? How does that compare against just a standard Bayesian IRL approach? We looked at 3 different cases. The first here is this idea that we have preferences over suboptimal demonstrations, and we have the same number of optimal demonstrations. We feed each of these demonstration sets into their respective algorithms. So Bayesian IRL and the Bayesian Rex. So we're kind of giving both of them what they expect. We also looked at what if both algorithms get just suboptimal demonstrations with preferences over them, and what happens if both algorithms get only optimal demonstrations. We found that Bayesian Rex performs on par or better than Bayesian IRL when they're both given the same number of demonstrations, and those demonstrations are the ones that the algorithms expect. Kind of naturally, we saw that given suboptimal demonstrations and preferences, that Bayesian Rex always performs much better than Bayesian IRL, even when we tried Bayesian IRL methods that were designed to work with good and bad demonstrations. And pretty naturally, given optimal demonstrations only, Bayesian IRL is kind of the clear choice here because Bayesian Rex is really designed to work given these preferences. And so I think it's interesting to kind of look at the landscape of problems and when you might choose one over the other. I think clearly if you have suboptimal demonstrations and preferences, then Bayesian Rex is a clear choice. If you have a fast MDP solver and optimal demonstrations, then I think Bayesian IRL is also the clear winner. However, in cases where you maybe don't have a good model, or when samples are really expensive to roll out in the environment, or you have a really slow MDP solver, I think the Bayesian Rex method is a really good candidate. And so to recap, we've proposed Bayesian Rex, which as far as we know is the first Bayesian reward inference algorithm to scale up to these visual imitation learning tasks. It's able to achieve really good performance on imitation learning for these complex benchmarks. And what's nice is it enables these high confidence bounds on performance. So we still haven't really answered the question of what an agent should do though if it has a high confidence performance bound that's bad. In particular, how can an agent kind of directly optimize its policy to be robust? So this is going to motivate the last section of the dissertation. We're going to talk about robust policy optimization and risk-aware active learning. And so one of the things we can do is we can query the expert for help if we want to try and optimize a policy to perform better. And this is work that I discussed in detail during my proposal. So I'm going to quickly just kind of give the highlights of how this approach works. So here we looked at this idea that a robot can ask for help. It can say, hey, am I doing this right? And ask for a critique of a demonstration. Or it can ask for a new demonstration and say, what should I do in this situation? And this fits naturally with what we talked about before, where we're able to calculate these high confidence bounds on performance. And in fact, we can actually do that over states, not just over a full policy. And what we can now do is just close the loop. So we can find states that have maximum value at risk, that have this high risk potential. We can then actively query for help at those states, add what we've learned from the queries to our expert demonstrations, recompute our posterior distribution, and then repeat this loop. We looked at several different domains. Here's an example of a robot learning how to set a vase in the center of the table, where it's given a highly ambiguous demonstration. The robot can reason about reward functions that are relative to the different objects on the table, as well as relative to the absolute position. So given this demonstration, it's unclear whether it should be between certain objects, or always on the table, or close to all the objects. And so what it does is it asks these risk-aware active queries in order to learn a policy that does generalize. And so it learns that it's supposed to just set the vase on the center of the table, regardless of where the objects are, but not hitting the objects. And what we showed is having these value at risk bounds are nice because empirically they provide really tight upper bounds on the actual generalization error on this held out set of tests, where we're plotting the actual and the predicted max placement error. And so one cool thing that could be an extension of this work is, given a specific safety threshold, we could potentially have a robot that knows when to stop asking for help. So given a certain number of demonstrations, it can say, okay, you can stop now. I'm now 95% confident that I've met your safety threshold. So this method has some downsides though. One is that it runs Bayesian IRL after each query. And currently, with this work, we were looking at just the classical approach, which is pretty computationally intensive. It also focuses on value at risk, which remember is this percentile bound. So like a 95th percentile worst case bound, which ignores the tail, ignores what's going to happen in like the worst 5%. And while it asks risk sensitive queries, it doesn't explicitly optimize the policy to be robust. In this work, we were just optimizing for the MAP reward function and then looking at our distribution in order to determine what our next risk-aware query should be. So what I'm going to talk about now is ways that we can directly optimize a policy to be robust. And this is some new work since the proposal. So there's a lot of existing work on these risk-sensitive approaches. Some of them are robust to small numbers of bad demonstrations. And I see this work as kind of complementary to our approach. We're going to propose an approach that takes a reward function distribution and seeks to be robust to that. And this reward function distribution could come from methods that produce posteriors that are robust to small amounts of noise in the demonstrations. There's also work that tries to match the risk sensitivity of a demonstrator. Our method that we're going to propose could potentially perform better than the demonstrator, rather than using kind of a GAN style approach that tries to try and directly mimic the demonstrator. We're going to look at ways that we can, perform robust optimization given this posterior, and potentially use the demonstrator as kind of a baseline from which we can try and perform potentially better. There's also a lot of work on this idea of kind of adversarial, worst case reward functions, where given a distribution or given some demonstrations, I try and find a reward function that's kind of pessimal, and then I optimize with respect to that. And we're going to propose an approach that instead tries to kind of balance these two objectives, balancing its risk as well as its performance. So we've talked about already this idea of value at risk, where here I've written out the actual math for what the value at risk is. It's the supremum. You can think maximum value of X such that my random variable being greater than that is going to happen with probability alpha. So if we look at our curve, we're going to assume that lower values to the left are worse. And so value at risk is the point where the area to the right is equal to alpha. So higher alpha means I'm looking at worse and worse outcomes. There's also this idea of conditional value at risk or average value at risk, which looks at how bad are things going to get conditioned on the fact that I'm worse than the value at risk. So looking at this 1 minus alpha worst case section, what's my expectation over my random variable? Where this random variable is some measure of performance. Now this is kind of the intuitive definition of value at risk, just this expectation of X's such that we're less than the value at risk. However, this only works for continuous distributions. We're often going to estimate our posterior via a discrete number of particles, such as MCMC. So it turns out there is a nice convex version of this, which works for continuous and discrete distributions. And because it's convex, it's going to make it easier to optimize. So our approach is going to assume that we have some reward function distribution that we want to be robust from. That's the distribution that's going to create this kind of performance curve. And so this could come from a lot of different places. It could come just from a prior that we have. It could be a posterior given demonstrations, like we've talked about a lot. It could be a posterior given demonstrations and preferences, like the T-Rex and D-Rex and the Bayesian Rex work. Or it could also be a posterior given a proxy reward function, R prime. And we're going to assume that we just have sample access to this distribution. So the question here is we want to optimize a policy to maximize our conditional value at risk. Well, we have some desired performance metric, which I'll call psi, that maps from the space of policies and reward functions to some scalar value that denotes performance. And then ideally, we want to find this policy pi that maximizes the conditional value at risk over this performance metric. And what's nice is we can actually do this via linear programming for discrete states and actions. And we take advantage of this one-to-one correspondence between stochastic policies and state action occupancy frequencies. So if we have a stochastic policy that takes action A and state S with some probability, we can also look at these state action occupancies. This is simply the expected number of times I'm in state S and I take action A. Given these occupancies, which I'll denote by U S of A, I can come up with a stochastic policy simply by renormalizing those weights, essentially, in order to come up with a probability distribution. Where the probability of taking action A in state S is just going to be how many times did I expect to be in state S and take A divided by how often I'm in state S. And so what's nice is we can formulate this using this dual form of a linear program to solve for an MDP. We have our reward, RSA, which is the reward for taking action A in state S. We have our state occupancies. We have an initial state distribution here, which tells us the probability of starting in a state. And then we have these transition probabilities that tell us the probability of going from state S prime, taking action A, and ending up in state S. And so this is often right here called the Bellman flow constraints, which essentially says that I look at how often do I visit state S, and that's going to be equal to how often I start in state S and how often I visit another state and then transition to state S. So we can take that and we can just formulate this where we replace maximizing the expected return with maximizing the conditional value at risk. And this creates a linear program, which can be solved in polynomial time to find the policy that maximizes our conditional value at risk. However, we also want to be able to balance risk and return. And so, for example, if we're like an autonomous car driving down the road and we see something in the road that we're not sure about, given that driving is a very risk-sensitive procedure, we probably want to run a different policy and completely avoid that box. Whereas if I'm a vacuum cleaning robot and I come across this weird carpet with spots, I could assume worst case, maybe it's a leopard, maybe it's lava, and I'll get melted if I get close to it. But likely, since I'm just in a home vacuuming, this is a lower risk scenario, and so I can act a little bit differently than this car that sees a box on the road. So how can we do this? We can simply just trade off this idea of risk and return, where we have conditional value at risk, and we have our expectation under our performance threshold. And we now give this parameter lambda, which allows a user to interpolate between being purely risk sensitive when lambda is equal to 0, or being just purely dealing with expectations when lambda equals to 1. And so when lambda is 1, this becomes basically just a general Bayesian IRL formulation. And what's nice, this is still a linear program, which enables polynomial time solutions. Whereas if we were to directly optimize for value at risk, turns out that's MP complete. So the last question we need to answer is, what should an agent be robust to? And so one of the things we can do is just have this generic robust formulation where we just look at the expected return of the policy under a reward function, random variable, and that's going to be our performance metric. We can also look at this idea of having a baseline, this idea of baseline regret that's common in the literature, where we assume that we look at the expectation of our policy as well as the expected return of some expert or some demonstrations that we want to use as our baseline. Okay, so I'm going to give now two case studies that kind of look at how this method performs. The first is the idea of just zero-shot imitation learning, where I have a prior distribution over rewards, and I want to optimize a policy. I have no demonstrations. This prior could come from historical data or perhaps from meta-learning on similar tasks. We're going to look at a classical problem from robust MDP literature called this machine replacement problem, where at each state, we're going to progress, the machine is going to age from 1 to 4. This is a simple problem, but the method will scale to much larger tasks. But for ease of looking at the problem, we're going to have these 4 states, and we have a choice of either replacing parts, which has a normally distributed cost, or the choice of doing nothing and just letting the machine age with the chance of the machine breaking down. And this cost is going to increase for waiting the longer that we wait. So the idea is, given this prior distribution, how can we optimize the policy? And what would the policy look like? I should note that these are gamma distributions, which have pretty long tails. And if we parameterize the gamma with these 2 variables, k and theta, which are these 2 values here, the expectation is just k times theta. So our expected cost for replacing a part is just going to be 100, whereas our expected costs for doing nothing are going to be increasing, but always less than the cost of replacing the part in expectation. And so if we look at a policy then that just optimizes for expectation, here in red, we see that it has very long tails due to the fact that it's kind of ignoring all of this risk about these potentially catastrophic outcomes and just focusing on average what it should do. Whereas if we tweak our lambda value and even just make it so 5% of the time we're kind of concerned with value at risk, and 95% of the time we're still looking at expectation, we can see that we're able to significantly truncate these tails, and we lose a little bit in expectation. We can also plot the sufficient frontier as we change lambda from lambda 0, being purely risk sensitive, to lambda 1, being purely return maximizing. We get this portfolio of different policies that we can evaluate that trade off our robustness and expected return. And you can see that, yeah, if we trade off a little bit of expected return, we can typically increase our value at risk by a significant amount, which is nice. We also looked at this idea of being robust to ambiguous demonstrations. So if I'm given a demonstration here where I have red states that have some cost or reward associated with them and white states that have some cost or reward associated with them, and I see a demonstration that starts here, takes a little bit of a detour around the red, and then goes to this exit state here in the bottom right. The question is, what can I do? And here we're going to use this demonstration as a baseline. And if we look at some standard approaches, such as a risk-neutral approach, like maximum entropy IRL, it's going to learn a policy that's stochastic. It's trying to maximize entropy. It's also trying to match the feature counts of this demonstration. And you can see sometimes it's going to go through red and take a detour. Sometimes it's going to dilly-dally in the white for a little bit, but eventually it will reach this terminal state. We can also look at one of these risk adversarial methods, such as this LPAL algorithm from Syed et al., where this is really solving this max-min optimization. Where it's trying to find the policy such that it's robust to the worst reward function that you could find. And this, as you can see here, is kind of the same baseline regret formulation. And in this case, it assumes, okay, red is probably like maximally bad, but white, maybe there's not a penalty to kind of dilly-dally in white. Whereas if we look at the baseline regret formulation of Broil, which is our method, this Bayesian robust optimization for imitation learning, we can see that as we change lambda, we're able to get this family of policies where when lambda is 0, we're extremely risk sensitive and we're going to avoid going into red at all costs, even if there is this shortcut here. As we increase lambda, we're more and more likely to be able to take this shortcut because we're bouncing off our expectation over the posterior with kind of the worst case. And so this gives us this nice family of distributions depending on how risk sensitive we want the agent to be. And you can see here, if we plot the sufficient frontier, maximum entropy and LPAL are not really reasoning about this posterior. And so in terms of the expected return robustness trade-off, they're much worse than this family of solutions that we're able to get. So in summary, we proposed this method called Bayesian robust optimization for imitation learning, which is efficient. It's got a convex objective, so it could be naturally extended to more gradient-based policy optimization methods. And it makes a policy robust with respect to this distribution by balancing conditional value at risk and return to give us this flexibility depending on the situation. So that summarizes the work that I've done for my dissertation, where we've looked at this question of how agents can efficiently infer the intent of demonstrators and provide these safety guarantees. I'd like to briefly go through kind of the main takeaways. So first we started with a general framework for safe imitation learning, where the main takeaways here are that we can come up with these sample efficient, high confidence performance bounds without access to the reward samples. This gives an imitation learning agent the ability to reason with high confidence about its performance when learning from small numbers of demonstrations, which is nice. However, as we showed, these methods can be computationally intensive. So then we turned to looking at how we can make these more efficient, where our main takeaways were that having pre-ranked demonstrations gives us this nice efficient reward extrapolation method that can lead to much better than demonstrated performance. And preferences from demonstrations can come from a variety of sources that we can take advantage of, either from human labels, watching an improving demonstrator, or via this idea of noise injection. We then looked at how we could scale up these high confidence performance bounds using this pre-training step, that pre-trains features, allowing us to scale to visual imitation learning tasks while still enabling these efficient high confidence performance bounds. And then finally, we looked at how to optimize policies directly to be robust. We showed that we can run these risk-aware active queries that allow an agent to know potentially when it's received enough demonstrations and come up with a high confidence performance bound, as well as showed that an agent can efficiently optimize a policy directly to be robust, given just a fixed set of demonstrations by effectively trading off this risk and return landscape. So yeah, so with that, there are lots of future directions. I'm gonna highlight just a few. There are more in the dissertation document. One is looking at just better policy optimization. We have a lot of methods that are really fast at recovering a reward function, but still require RL at the end to come up with the policy. I think model-based reinforcement learning would be a natural fit to here, so we have efficient reward inference as well as policy optimization. In terms of feature pre-training, I think there's lots of remaining work to be done to improve this, such as leveraging recent work on contrastive learning, self-exploration to get a wider variety of data for learning these latent spaces. We can also look at scaling up this idea of robust optimization, where we could try and combine our ideas from Bayesian recs with these ideas from robust policy optimization and plug these into a state-of-the-art policy gradient method or reinforcement learning methods such as soft actor critic. And I think there's lots of interesting human factors problems as well, such as what's the best way to obtain these preferences over a variety of demonstrations, and if we're able to actually learn from humans by watching them if they're learning at a task. And I think a lot of work also revolves around this problem of explainable AI, where a lot of times a risk-averse policy might be kind of hard for a human to understand why this is a robust policy. So I think looking at intuitive ways for agents to explain their belief distributions and to convey these risk-return trade-offs to a human is really important if we want to have these systems that can be trusted in the real world. So with that, I'd like to thank my collaborators, especially my advisor, Scott Neekum, my lab mates, as well as people I've collaborated with outside of UT. And yeah, I guess I'll turn it over to questions now. Thank you.